then why not use something like liquid nitrogen to cool it down, to refrigerate it? So here I have a traditional container for hot gas. And what we're going to do is to put it into the liquid nitrogen to cool down the atoms and molecules so they will be moving more slowly. Okay. It's beautifully dramatic, isn't it? So, in the answer to one of the questions, Eugene Polzig said, if you want to have a lot of fun and gather young people around you who want to play, then go into research. That's why we do it, because it's so much fun. Okay, so let's see what happens with that. Over here, I have another container for liquid nitrogen, but it's empty. Okay, it's been sitting out at room temperature all day. That means that compared to the liquid nitrogen, this container is burning hot. It's like it was red hot. And what I'm going to do now is to pour some liquid nitrogen from this container into this one. Imagine what would happen if you had a metal bucket and you heated it up until it was red hot, and then you poured cold water into it. It would boil, and that's what's happening here. Now, just since I know I'm going to need a little bit more, don't try this at home. Okay, so now, while that's cooling down, let's cool down some more gas, because of course if we want to do experiments with cold gas, we want to have plenty. Okay, I hope I didn't make it too big. Okay. No, there's plenty of room in here. Okay, there we go. Perfect. Okay, let's go over here. Now, okay, the boiling has subsided. That means the inside of this dewar is down to the temperature of the liquid nitrogen. And I'm just topping it up there. And now, let's take this nice fresh flour. Nice fresh flour. It's been sitting out at room temperature all day. Compared to the liquid nitrogen, this flour is burning hot. Imagine that you took a fireplace poker, a metal rod, and heated it up in the fireplace until it was red hot. And then you took it out and you plunged it into a bucket of cold water. What would happen? It would boil. And that's what's going on here. The flour is making the liquid nitrogen boil as the flour cools down to the temperature of the liquid nitrogen. So, what was the color of the last balloon that went in? Let's try a blue one this time. Because we want to have lots of cold gas. Okay. Here we go. No problem. What? That's the trouble. You see, when they give you demonstration tables, they think it's cool to have the front covered up so you can't see what's going on. No, there's nothing under here, you see. No tricks. Okay, let's go over here to the flour. Now, the flour it's now stopped boiling, which means that the temperature of the flour is now down to the temperature of the liquid nitrogen. So when I take it out, it is frozen so hard that I can break it like it was made out of glass. This stuff is really, really cold. And if you've got something that cold, then you might as well use it. What? You might as well use it to cool down your gas to make the atoms and molecules move more slowly, because that's the whole point. We want to make the atoms and molecules move more slowly so it'll be easier to measure their ticking and we can make a better clock. Okay, wonderful. Now, what else can I do to show you how cold this stuff is? Okay, here I have a plastic bottle. Now, I'm pretty sure that when your mothers were explaining to you the proper procedures for cooking things in the kitchen, one of the things they told you was never ever take a closed container of liquid and put it into the oven. Well, here we have some liquid. And a little bit more, just to be sure. Okay. And now I'm going to put the lid on very tightly. And compared to the temperature of the liquid nitrogen, this room is an oven. And so I'm going to take the bottle and put it into the oven. Now, let's see, what else can I do to show you how cold this stuff is? Yeah, here we go. I have a nice, bouncy rubber ball. So I'm going to take the rubber ball and put it into the liquid nitrogen, and we will see what happens. While that is cooling down, how about this? This is a rubber band. Nice, stretchy rubber band, okay? Let me take the rubber band, put it into the liquid nitrogen. The rubber band is hot, right? It's going to do the same as everything else. It will make the liquid nitrogen boil, and then I just wait until the boiling has subsided. That means the liquid nitrogen has cooled the rubber band down to the temperature of liquid nitrogen. I can break it like it was a dry twig. When I warm it up in my hands, it's a nice stretchy rubber band again. This stuff is really, really cold. How cold is it? Well, unless you've been in a low temperature physics lab, then I'm guessing that this is the coldest stuff you've ever seen. How cold is it? Well, to explain how cold it is, we have to think about how physicists like to measure temperature. Now, for everyday temperatures, we measure it in degrees Celsius. When it's freezing, it's 0 Celsius. Maybe we get pretty cold here in Copenhagen. It may go to -10. It may even go to -20 sometimes. Physicists don't like these negative numbers for temperature. And so we use a temperature scale where the lowest possible temperature is 0. And on that temperature scale, the Kelvin temperature scale, which we tick off in Celsius degrees, room temperature is about 290 some degrees, almost 300 degrees. Ice melts at 273. The coldest temperature anyone ever measured on the face of the Earth was someplace in Antarctica in the winter, and it was 185 degrees above absolute zero. The coldest air temperature anywhere ever on the face of the Earth was 185 degrees. This stuff, this marvelous stuff, that boils when I pour it out on the ground because the floor is so hot compared to it. This stuff is 77 degrees above absolute zero. 77 degrees above absolute zero. Really, really cold. Let's have a look at the rubber ball and see how we're doing. Okay, let me pull it out. There it is. Now you remember how nice and bouncy this rubber ball was? It breaks like it was made out of porcelain. This stuff is really, really cold. And it seems quite reasonable if you've got something that's that cold that you would use it to cool down your gas, which is what we've been doing. But it seems that some of you may have noticed there was something a little wrong here, that the volume of the balloons that went into this container was larger than the volume of the container. How is that possible? And the reason is that these balloons are now as flat as pancakes. In fact, they're sort of like Frisbees. And so how many went in? 4. So 2 reds and 2 blues. Okay, great. How many green ones did I put in? A few more. Here we go. That one might explode. You might want to be careful. Now, there's still more in here. This is great. So what was going on here is that the balloons got flat. Whoa! The balloons got flat not because the air went out of them, but because the air condensed. And you see, it doesn't matter what kind of gas you get, if you put it into a container and then put the container in contact with a really cold refrigerator, if the refrigerator is cold enough, then the gas will condense into a liquid or a solid, or it will stick to the walls of the container and... Whoa! Fantastic!